We often treat the firing architecture of a neural network and the rigid grid of a magnetic alloy as two separate worlds. This diagram shows the overlap, where the energy function, E of S, unites Hopfield networks and spin glass. Associative memory and disordered magnetism are governed by the same mathematical engine. In computer science, this relationship is frequently described as a biological metaphor, a conceptual shorthand for how data is processed. The bottom row of this table clarifies the reality. The Hopfield energy function is an Ising Hamiltonian, a rigorous equivalence from statistical physics. This mathematical equivalence allows us to identify the physical limits of artificial memory and see how data structures degrade under pressure. To understand this connection, we have to start with the foundational unit of a Hopfield model, a binary neuron that exists in either an active or inactive state. This row compares the binary neuron concept to the Ising spin, both restricted to states of positive or negative 1. Moving down, we see how these units interact. In AI, neurons communicate through a synaptic weight, while magnetic spins use exchange interaction. These interactions follow identical rules. A positive connection leads units to align in the same state, while a negative connection causes them to anti-align. Since the variables and interaction rules are interchangeable, the behavior of both systems is driven by the same physical laws of energy. Those physical laws dictate that every network state has an energy cost, calculated by a Hamiltonian energy function. This equation calculates the total energy of the network based on the symmetric connection matrix and the states of interacting pairs. The text on this chart explains the fundamental law. The system will universally attempt to roll downhill to minimize this total energy value. The shape of that terrain is sculpted by connection weights assigned through Hebbian learning. This mathematical rule connects the principle of neurons firing together to positive connection weights for frequent coactivations. When the network stores a memory pattern, the math carves a valley into the energy landscape. A stored memory is a disguised ferromagnet, a topological attractor state that draws in nearby data coordinates. We can test the network's function by feeding it a noisy or corrupted image. A noisy input places the network at a high-energy coordinate. Using the local effective field, each neuron flips its state to agree with the local majority, lowering total energy. The system slides down the topological gradient into the attractor minimum. In a Hopfield network, memory retrieval is a process of controlled energy minimization, where data settles into the nearest attractor. If one memory creates a valley, we must determine what happens when multiple memories have conflicting pixel instructions. This diagram illustrates magnetic frustration. In this triangle, it is impossible to satisfy the constraints of both alignment and anti-alignment simultaneously. As the text explains, competing memory patterns cancel each other out, producing random, frustrating couplings that cannot be resolved. This frustration warps the global energy landscape of the neural network. Maps 1 and 2 show distinct valleys where associative memory functions normally under low load. As load increases, frustrated connections grow and the terrain shifts. Map 3 reveals an overloaded network degenerated into a spin glass topography crowded with false valleys. Overloading the information capacity completely destroys the physical terrain, turning useful attractors into an inescapable trap of false, hallucinated memories. We track this capacity using a loading ratio, the number of stored memories divided by the number of neurons. This chart shows the absolute limit of storage capacity. When the ratio reaches approximately 0.138, memory retrieval fails entirely. Crossing this mathematical limit marks a sudden, catastrophic structural transition, where the entire network's internal organization completely collapses. To diagnose the state of the system, we use specific thermodynamic parameters. This formula defines the overlap parameter, which measures similarity to a true memory. A value near 1 represents successful recall. The Edwards-Anderson parameter measures frozen disorder. A value above 0 indicates the system is trapped in a stable configuration. By analyzing these two metrics, we can diagnose the physical state of an artificial brain exactly as a physicist evaluates a metal alloy. In the retrieval phase, overlap is high, and memory recall works as intended. In the spin glass phase, overlap hits zeros, but the network remains frozen in a stable state. At this stage, the network has physically frozen into a random configuration that is stable but functionally useless. A functional Hopfield network is an Ising-like machine that retrieves data through energy minimization. Overloading that machine rips apart its landscape, forcing a phase transition into the jagged, frozen terrain shown on the right. The associative memory of artificial intelligence and the disordered magnetism of the natural world are unified by the same mathematical engine.